So our last speaker is Ruben van Belle, and he will speak about Radon Nikodym derivatives and martingales. So please go.
Yes, thank you, and thank you to the organizers for organizing this event. So yeah, I'm going to talk about two things: Radon Nikodym derivatives and martingales. So those are things in measure theory and probability theory, and I'm going to try to say something about what's happening categorically with these two things. Okay, so the first part is going to be Radon Nikodym derivatives, and then the second part, martingales. So I'll maybe start with reminding you what Radon Nikodym derivatives are. So it's a thing in measure theory. So yeah, let's start with a measurable space. And let's look at two measures on this space. So a sigma finite one and a finite signed measure. And in such a way that this one is absolutely continuous with respect to this other measure. So what that means is the following thing. If mu of A is 0, then nu of A is 0 for every measurable A. Okay, so if that is the case, then we can represent nu in the following way. So we can, there exists a mu almost surely unique integral map such that we can write nu as integrating f over A with respect to mu. Okay, and this is the Radon Nikodym theorem. So then what are Radon Nikodym derivatives? So those are exactly those kind of f's. So that's the Radon Nikodym derivative of nu with respect to mu. And the notation for that is like this. So you can see the d mu's sort of cancel out. Okay, another way of looking at this is we can look at the following map. So if we look at mu almost surely, or equivalent classes of mu almost surely equal random variables that are integrable, we can send such a random variable to a measure in the following way. So again, by integrating over subsets, and that is going to be clearly absolutely continuous with respect to mu, then the Radon Nikodym term is saying that this is a bijection. Okay, so some examples. Why do people care about these things? So you can look at the standard normal distribution on the real line and the Lebesgue measure. The Lebesgue measure is sigma finite. Standard normal distribution is it's a probability distribution, so it's definitely finite. And is absolutely continuous with respect to lambda. So there is a density function. Of course, I guess in reality, you define the normal distribution using this density function. So you don't really need the Radon Nikodym theorem, but this is still a Radon Nikodym derivative. So yeah, it definitely is something relevant, these Radon Nikodym derivatives. Another example has to do with conditional expectation. So if we fix a probability space, so a set, sigma algebra of subsets and a probability measure on that measurable space, and if we look at a sigma subalgebra, G, so if we have those things and we look at a random variable that is measurable with respect to the bigger sigma algebra, then again we can define a measure by integrating over A's, and we interpret this as a measure on G, on the smaller sigma algebra. So okay, this defines a measure, and this is just other notation. So okay, so then we can verify our conditions from the Radon Nikodym theorem. So if your P of A is 0, then if you integrate over a 0 set, that's going to be 0. So okay, nu is absolutely continuous with respect to P. So that means there exists a P almost surely unique and now G measurable integral map F such that integrating over G measurable subsets is the same. And again, different notation, you can write it as this. And this F is called the conditional expectation of X with respect to this sigma subalgebra. And the notation for that is this. So that's also something that's used quite often in probability theory, especially martingales. So in the second part, we're going to come back to this. But okay, those are two examples of Radon Nikodym derivatives and why we care about them. So now I'm going to give a very short proof of a very special case of this result. So namely for finite probability spaces. So let's look at a finite set with a probability measure on that set. And let's look at a measure that's absolutely continuous with respect to P. Then I'm going to define a map F from A to R as follows. So okay, when this is not 0, we can divide by it, and otherwise, if P of A is 0, then Q of A has to be 0. So then we'll just take this to be 0. And then, well, you can just easily check or verify that this is the Radon Nikodym derivative. This gives you the map that you want. And yeah, because this is almost surely the inverse of multiplying by P, right? That's the reason behind it. Okay, so now I'm going to start talking about category theory. So the ideas, we're going to take the finite version and we're going to extend that to the general version. So the category I'm going to look at is prop, as probability spaces as objects, and measure preserving maps between them. Yeah, I'm going to define some things now. So fix a probability space. I'm going to call this space of all measures. And with measure, I always mean now finite positive measures that are bounded by n times p, and n is just a natural number here. And I can give a metric, so the total variation metric, so that becomes a metric space. And I'm going to call that mn of omega, where m stands for measure. And I'm going to define random variables on omega as well. So these are just measurable maps from omega to 0, 1, 0, n, and we identify them when they're p almost surely equal. That's a probability measure. Yeah, well, now I'm using probability measures. Yeah, so and this mu is a measure. So does that clarify it? Sorry, this one or?
Yes, the P.
This P is a probability measure.
And the other is another measure.
And this is a measure. Yeah, so the probability measure is fixed. So yeah, these random variables, we can also give that a metric, the L1 metric, and for some reasons we multiply that with a factor of half. And these are complete metric spaces. So yeah, you can use the Ries-Fisher theorem for that. Well, I guess that's sort of literally saying that these are complete. If we're looking at finite probability spaces, which is what we're going to do, then you don't need a big theorem, so then you can just prove that as a sort of an exercise. So I'm also going to define something on maps. So if I have a measure map between finite probability spaces, then I can define a map like this by pushing forwards every measure on A along my map. That gives you a measure on B. And I'm going to also define a map here by sending a random variable on A to this random variable that's defined in this way. And you can check that this is well defined. So if something is almost surely equal to G, then this is going to be almost surely equal to this one. And these are Lipschitz maps. Okay, so those were all definitions, but what did we actually define? We defined two functors like this on finite probability spaces, two complete metric spaces. Yeah. So then what did our finite version of this Radon Nikodym theorem say? We can really interpret that as that these are isomorphic. That follows almost immediately from that. Okay, so now we have this, and now I want to can extend these to all probability spaces. So that's what we're going to do, and well, because these are isomorphic, well, the can extensions are also going to be isomorphic. So now we need to figure out what these can extensions are. So yeah, if we fix a probability space, omega, then we have that, well, the measures on omega, like I defined before, are indeed, well, correspond as to the right can extension of this functor evaluated in omega. Okay, so why is this true? So I'm first going to give like sort of an intuitive ID, maybe, sketch of the proof, and then a more detailed. So, well, for right can extensions, we have this end formula, right? So if we ignore this integral sign for a second, then we have maps from this to this. And these are, well, since A is just finite, these are really A-indexed measurable partitions. And these are measures on A, but A is finite, so these are A-indexed real numbers. So we're sending, well, measurable partitions to real numbers, so that's already close to a measure, right? So if we then put the integral sign back, that's saying that, well, these maps are behave in a coherent way, and that will then imply sigma additivity. A more detailed version of the proof is, well, you'd first define maps from this to all these maps by pushing forwards along these maps from omega to A. Well, that gives you this map, or maybe better, this space together with these maps form a wedge over the functor we're taking the end of. So it's a wedge. Now we want to show that it's a universal wedge. So to that, take another one. And so yeah, that means we have map from Y to this for every finite probability space A, right? So it's for every finite probability space, so we're going to fix some special finite probability spaces, namely the following ones. If you have a measurable subset E, then we're going to look at this probability space where the underlying set is just these 2 points. And in that case, the indicator functions become measure preserving. Well, and then using all this stuff, we can define, well, we can assign to every measurable subset a real number. And then because this is a wedge, this is going to be, well, firstly, finitely additive, and then because everything is bounded by a measure, it's also going to be sigma additive, which is then going to give you the universal property. So that's very short, the proof, but I want to give you the proof to show that I'm not really using anything like special measure theory results or anything, just like sort of a straightforward categorical proof. Then for the second part, it does require some measure theories. So the second part is, or the second proposition is saying that we have the same for the random variables. So the right can extension of this finite version of the random variables is indeed giving you the random variables that we want. And that does require some measure theory, which I'm not going to say more about, but yeah, the measure theory didn't just magically disappear. So that's sort of, yeah, going on here. Okay, so now we can combine all the things we have so far. So we have this space of measures. Well, that's by definition equal to this. Then we just showed that that's equal to this right can extension. Then because on the finite level, they are isomorphic. Well, the right can extensions are going to be isomorphic as well. And then with this last proposition, we have the last line as well. So that gives us the results, at least for when things are bounded by NP. So that's stricter than absolute continuity. But to fix that, we can take the co-limit over all n of both things. Well, the co-limits are going to be isomorphic as well. And that's then exactly going to be this. So then we have the Radon Nikodym theorem. Yeah, so maybe to finish this last part, to finish this first part, a last remark. So, well, we described what these right-hand extensions are doing on objects, right? But I didn't really say anything about what it's doing on morphisms. So, well, because they're right-hand extensions, these morphisms are defined by a universal property. So it's these maps. Yeah, I use this notation to avoid writing right-hand extensions the whole time. But these maps are the unique maps such that they commute for for a bunch of triangles. So because it's for all finite probability spaces, again, we can look at these sort of special kind of finite probability spaces, which we used before. Well, then these commutative triangles give us this. And if you then stare at these for a few minutes, then, well, you can figure out that that exactly means this. So we have pushing forward along G, and then these conditional expectations, which I talked about before. So I thought was, well, cool that these appeared, because these conditional expectations are sometimes a bit difficult to work with, like the existence is not trivial. Usually you cannot really construct them. So I thought it was nice that they appeared from these universal properties. Of course, it's also not a complete surprise, because I showed you earlier that they do follow from the Radon Nikodym theorem. But yeah, that's how conditional expectation also appears here. Okay, so to summarize this first part, we had a finite version of the result. We extended it to the general result. And on the way, we also found these, or recovered these conditional expectations. Okay, so that's the first part. Then the second part's about martingales. So I'll start by telling what a martingale is. So again, fix a probability space and fix a lot of, or like a collection of sigma subalgebras that are directed, and in such a way that their union as sigma algebras, or their colimit, I guess, is the whole sigma algebra. Then a martingale is a stochastic process. It's a collection of integrable random variables such that xi is only measurable with respect to this smaller fi. And such that we have this martingale condition. So taking the conditional expectation of xj with respect to an earlier sigma algebra gives you the earlier random variable. Okay, so these are martingales. Maybe to very quickly motivate martingales, why are martingales important? Well, the most important stochastic process, Brownian motion, is a martingale. So that's maybe a reason to motivate martingales as well. So what do I want to talk about for the last part now is this martingale convergence theorem. So I'll say what the martingale convergence theorem is, but I'll first remind you of this easier result that, well, every bounded monotone sequence in the real line converges. Then the stochastic analog of that is the martingale convergence theorem. So it says that if you have a martingale that's bounded in some way, it converges to something. There's a different version of that as well. If it's even more bounded, then it converges even stronger, and we can even represent xn as conditional expectations. So what does this mean in?
So can you go back one slide? Your martingales are indexed over n?
Yes, now
So
they are.
it's not like a continuous process, right?
No, yeah, now I'm focusing on discrete processes.
And should I interpret convergence as some sort of a stationary condition after a while or something?
Sorry.
Like the fact that it converges to a random variable is telling me that the process is stationary after a while, like it becomes stationary?
Well, it's sort of convergence of functions, right? So it's in this, it's almost surely pointwise convergence. Here it's convergence in a certain norm. So yeah, well, if this is constant, maybe then I guess you can interpret that in that way. But that limiting random variable doesn't have to be constant or anything.
Okay, thanks.
Okay, so in terms of category theory, how would we describe this? So all these sort of restricted probability spaces form this diagram. And then the space where we started with is the limit of this diagram. I think that's not too difficult to see. So now suppose for a second that that is Mn, just this functor of, sorry, this should have been an RV. Okay, so this M is an RV. Suppose that this RVn preserves this limit. Then what would that mean? Okay, first of all, it means this. And then this is a limit of complete metric spaces. So the way we can calculate that limit is, well, the underlying set is the same as calculating limits in sets. So then for any co-filtered limit of sets, you get something like this. But then a few slides ago, I told you that this RVn acts as taking conditional expectation, right? So that means this condition translates to this condition. But this is just exactly saying that our stochastic process has to be a martingale. So, well, we can interpret this isomorphism then as saying that for every martingale, such that they're all bounded by n, so we're still working with these bounded by n conditions, there exists something in here, a random variable, such that this condition holds. In the case where we're using this very strict boundedness, this condition will immediately, well, not immediately, but in a few lines of proof, imply the convergence as well. Okay, so what we want to show is that this RVn preserves certain limits. So the setting we have so far is not completely going to work. Well, it is definitely going to preserve these limits because, well, the martingale convergence theorem is true. So it should preserve limits, but I want to prove it in a more categorical way, right? So this setting is not exactly going to be the right thing. So I'm going to change things a little bit, but I'm not going to say much about it. I'm going to enrich everything over complete metric spaces. And then I claim that everything we said in the first part still works, where everything is enriched over complete metric spaces. I'm not going to say a lot more about this, except for something you might be wondering right now: how do I enrich prop over complete metric spaces? So I'm going to look at sets of measure-preserving maps, and I'm going to define this pseudo-metric. So it's really a pseudo-metric. So I actually need to change this maybe to pseudo-metrizable spaces. And I'm going to take the completion if this is not complete. If our codomain is a finite probability space, and we have completeness. Otherwise, I take the completion. So okay. There's some details I'm not telling you, but modulo some details, this is still working in the enriched context. Okay, then the sort of categorical proof of this martingale convergence theorem. We always have, for categorical reasons, a map like this. Because remember, this omega was the limit of these omega i's. But in general, this is not an isomorphism. But in this case, because we're working in complete metric spaces, it is. So this is a co-limit of complete metric space. So that means we need to take a completion as well. So it's bigger than the co-limit of just metric spaces. And well, because this set is dense in this set, so that is by a lambda argument, you can prove that. It follows that in this case, in the enriched version of things, this is going to be an isomorphism. Okay, so what do we then have? RVN was this equal to this right Cannon extension, so this N formula by, well, what I said just now is we can take out the limit and that becomes a co-limit. Then for categorical reasons, this co-limit becomes a limit. And we can also take that out of the ends. And then we have, that this RVN preserves the co-filtered limits, which is what we wanted because that translated to the martingale convergence theorem. And then an interesting remark maybe here. I never really used anything special about this functor RVN, right? So I could also do everything for the other functor MN. That would also have given something, or well, other functors. So I guess, I found an interesting observation. And then this is sort of the final summary. So I'm going to stop here. Thank you.
Questions or comments?
Hi, thanks for your talk. I have two quick questions. The first one is on the first half of your presentation. It's a little technical thing, but I was a little bit puzzled. At some point, you have a colimit. Sort of, you pass something to a colimit to prove a statement. I think you have this subset of the measures that are bounded by NP, and then you take the colimit over N, and you stated that that's the same thing as being absolutely continuous. If I remember correctly.
That is what I said.
This one here. Is it obvious that if something is absolutely continuous with respect to P, it must be bounded by NP? Are these finite measure spaces or not?
So I guess I should have said I'm taking colimits in complete metric spaces again. So there's a completion going on. So I guess that's why we can push.
No, but even just in terms of measures, like if I know that mu of A is 0 whenever P is 0, like does it have to be bounded by NP necessarily?
No.
And so why is the colimit? Why do you get absolutely continuous measures if you take the colimit of those?
Because
things?
that's because we're taking colimits in complete metric spaces. So there's a completion. So it's not just a union, but it's like the union and then completed. So that's why it gets
that's the thing.
more
okay,
than
okay. Because I thought it was just the union and it wasn't.
So there's this completion. Thank you. I didn't really say that, but that completion is giving us.
Okay, thanks.
This.
And the second one is you have this formal way of dealing with processes that are martingales. Can you also incorporate some drift in your processes with using this machinery, or is there something interesting to be done in that case?
I haven't really thought about that. I also don't really know that much about drift in stochastic processes. I don't really know the details about that, so I cannot really say anything useful about that. Sorry.
Okay, thanks.
Thanks for the talk. And I have a kind of related question. Are your metric spaced generalized metric spaces? Because I see you compute colimits, I guess, with usual metric spaces. You don't have all of them.
So I think.
So do you allow the distance to be infinite? I guess that's what I mean.
Yes, I think we don't need to. Maybe I've missed the detail, and we actually do need it at some point. But in most of the things, because we have this boundedness condition.
So maybe the limits are good enough so that.
So the metrics are also going to be bounded maybe by 2n or something like that, or some function of n, so that you have diagrams that are where all the metrics are bounded by the same number, and then of course you can take
makes sense.
The colimits. But otherwise I guess I should have worked with generalized metric space, but I think it should be fine like it is right now.
Thanks.
Other questions? I have one. in recent years, there has been a lot of work about new categorical approach to probability, using the language of Markov categories and their graphical formalisms. Do you think that it could be possible to present your results and instruments in this setting and maybe providing graphical proofs of these theorems?
So yeah, I haven't really thought about that, but I guess these conditional expectations are very similar to like the Markov kernels and the maps. That well, you think, you look at the maps in the Markov categories like Markov kernels, right? So I guess in that sense, you can maybe say something about a Markov chains and things like that. Maybe prove some convergence results for those as well. I wouldn't know what that looked like using string diagrams or something, but there might be something similar going on.
Thank you.
Yeah, just to add to your question, even if you don't look at string diagrams, there is this whole way of thinking about categories probabilities in terms of channels, states, predicates, like the work of Bart Jacobs and other people. And this work also, he has papers on this Radon Nikodym theorem seen in that fashion. So I don't know if you're aware of these things. Is that something you've looked into?
About the Radon Nikodym theorem itself, I haven't really seen much.
Well, I suggest you look it up because there are papers in which he proved, other people, including also myself, proved some results in this vein. And it may be just useful to compare and see.
Yeah, no, thanks. So, and that's Bart Jacobs.
Bart Jacobs, if you look up his page, there is all kind of papers that, and many of them have a good intersection with what you're doing, I think.
Okay, great. I'll definitely look that up. Thanks.
So let's thank the speaker again. Unfortunately, the other speaker is sick, so this was the last talk of today. So I want to thank all of you for being here, and Buon Natale.